Yeah, hello everyone. Today we have finally last discussion related with modeling session. Actually, cluster topical session 2, it's modeling. We have 4 speakers related with modeling of solid state battery. Actually, we can discuss about electrolytes, anode and cathode, and cell in general. First speakers from CA, Herne Manzanares, it's correct, and he present today's result from Astrobot. So yeah, welcome.
Thank you. So I will talk about hybrid electrolyte and different microstructures that we have tested in Astrobot project. So this is it's a frame for a lot of banality in battery technology. We want increase the energy density and so use lithium metal, and we need solid electrolytes. So we have globally 2 family of electrolytes, so polymers and inorganic ceramic. Polymer has very low conductivity, and I'm very nice with ceramic in this topics because I say it's close to conductivity of liquid, but I guess it's a little less. To explain rapidly the difference between both, for polymer we have a matrix of macromolecules. We have different states of these materials, so we can have viscous compartment on glassy and rubbery. And we have different displacement into this matrix. So the macromolecule can't move totally in the melt if we don't have links between the molecules. And we have deformation, flexion, and torsion of the segment of this molecule. So for the lithium into this matrix, lithium need a coordination site to move into this matrix. So we understand for what lithium don't move very fast into a polymer matrix because he needs the conformation of a good conformation of polymers for have this coordination site like this point. So this matrix have a good adaptability of mechanical stress, but poor ionic conductivities. For ceramic matrix, we have not the same displacement of lithium into the domain. Now we can imagine that we have a lithium that jump into site, void site into the ceramic, and we have a conductivity, path conductivity of lithium here. So we can have a higher density of lithium into ceramic, maybe 14 mole by meter square. And we have a good frequency on jump, so a good diffusion of lithium into the ceramic. But the problem of the ceramic, it's the tribology behavior at the interfaces with the active material. We have interfaces difficulty to have a good stability. So the idea in this topic is to have a hybrid electrolyte, so have the good property of diffusion of ceramic and the good mechanical property of polymer at the interfaces. That is very banality of trivial stuff to explain the idea. The idea of the model, it's a classic idea. So we have a mechanical compartment at the very low scale. And the experiment that we use, it's electrochemical stuff or something. So you need a very large time scale and space scale. And it's very hard to link the two domains. So we use the continuity equation to help thermodynamic and average collective particles. So we will modelize the fluctuation of concentration and the current of all of particles into the material. So that's the model that we use into the Astrobot project. It's a conventional model on electrochemical works. And concerning the result, we try to modelize So a block of polymer material, and we put into this block spherical particles of ceramic in this first study. So for example, here we try to modify the quantity of ceramic. So we take LZ0 and we have the same radius of particles, and we modify the quantity of particles. And in this simulation, we have the same quantity of LZ0, but we don't have the same radius of particles. Concerning the result, maybe the problem, we try to modelize a very, very good conductivity of ceramic. For example, the ratio here, it's the conductivity of ceramic versus the conductivity of polymer, and we try to simulate with this ratio of 100. And when we have 60% weight of LZ0, we have only multiplied by 2 the gain on conductivity. So in this model, we don't have contact between particles. So all of particles are not percolate into the structure. And in this configuration, we can put a lot of ceramic, and we don't have a huge gain of conductivity. For the second point, when we change the size of the particle, so more particles are bigger, and less are surfaces. We don't have a strong modification of this. I guess it's the same. So the size of this particle in this configuration have not really huge importance. The second part of the result, now we don't use spherical particle, but we try to have sticks particles, because I try to do that in the experimental point of view in this project. And we try to simulate what is the size of the radius of these sticks. And that we can see there are no effect of the size of the sticks. The effect is only defined by the quantity of the sticks. But the interesting point of view here, it's we have only a ratio of 10 for the conductivity. So the ceramic the ceramic conductivity have 10 more than polymers. And for this configuration with sticks, we multiply by 2 the gain, which only even think 25%. Sorry. So it's better than 16% previously. So the structure of sticks have a good advantage because we can have the same effect for less ceramic materials. But if we try to do this simulation with not now with vertical sticks but horizontal sticks, we don't have the same gain. And for 25%, we have very close to a polymer matrix. We need to go to 50% for have a small gain. So the idea now it's said to us to have this type of configuration when we need to put ceramic material, but have a very structural form of ceramic percolation of particles in the side of the polymer of the system. And for finish, we try to simulate the mixing configuration to see exactly the same way. And the idea is the same, because when we put ceramic into a material, it's a little chaotic. So we try this, and that we say we need to have a good orientation of sticks for have a gain effective. So that is the result of this project. So the conclusions, it's so we have a gain of conductivity if we put ceramic into polymers, but the gain is very low, I guess. We need a percolation between particles. If we had no percolation, it's not efficient. And we need probably a very strong rate of particle for have a good gain of conductivity, but we need to confirm that we have a good mechanical property after. That's you.
Thank you so much. Yes, thank you so much for your presentation. We have time for question answer. If you have some question from audience or maybe online, please.
Thank you. Thank you for the presentation. I'm wondering if the model also incorporates some surface-enhanced diffusion, for instance, in the polymer matrix itself. So you have the bulk ceramic conduction diffusion, but does it also include surface diffusion alongside the grains, alongside the ceramic?
Yeah, we can imagine they had a better diffusion just aside of the ceramic. And in other projects, we try to see that because they are theory, but we can't confirm that. I guess the problem is to have a good experimental validation of this result, and it's not clear if we need another hypothesis like this.
Okay. Thank you.
Okay, thanks so much for presentation. I have, one question. Your work related with theoretical aspect because you consider about different, for example, thickness, size, and so on. It's possible, or maybe you can consider implement a practical application. Maybe your partners think about it, or maybe try it. I don't know.
Sorry, I don't understand.
No, I mean you consider your methods modeling for electrolytes. It's quite interesting for solid-state battery community. But for theoretical work or also like plus practical work?
That is theoretical yet.
But you consider maybe, I don't know, implement in practical. So maybe your
Yes.
partner tried or not?
Yes, maybe I can answer.
Okay.
We did it also, so with LATAT, which is based in Spain, we can produce this LLZO by electrospinning. So we could see a high increase of ionic conductivity when there was no ionic liquid used. But when we used ionic liquid inside the electrolyte, we could see that the ionic liquid has the most influence on the ionic conductivity. So addition of LLZO or not did not improve so much ionic conductivity because of the presence of ionic liquid. But yes, it was also done in practical.
Okay, great. Thanks so much. Yeah. Thanks so much again for your presentation. Okay, next speaker, it's related with cassette modeling. It's also quite interesting. And Mona Safari from Hasselt University, present of Solidify results.
Thank you so much. Good afternoon, everyone, and it's a pleasure to be here, learn about you and learn about the type of work you're all doing. The presentation, actually, I don't go to kind of introduction about the materials because our partners and colleagues, Corsin and Amelia, properly describe the scope of the project and materials involved. In the first part of presentation, I am basically talking on behalf of the colleagues in the from GMATI Technology, Matthew, which I think he's also connected online, couldn't be physically present, about the work that they did on the microstructure, modeling of the microstructure of cathode, trying to come up with quite detailed representation of microstructures, composite electrode, porous electrode in general, but of course when they are also impregnated with the solid electrolyte. And the architecture of the elements or the sandwich layer that is usually simulated is general and is a lithium anode electrolyte and then cathode. But the focus of this work is basically trying to go into the details of the porous cathode, and then lithium and electrolyte could be a little bit considered as a homogeneous, let's say, element in this kind of modeling. So, and that's about the structure and the basically the boundary conditions or initial conditions that considered in this still a kind of macroscopic type of modeling, and then the simulation also simulations were done in the environment of CAMSOL multiphysics. And then the idea was also because the final goal is to apply these detailed microstructures in the simulation of the solid-state batteries. Therefore, it necessitates to also couple multiphysics, considering the mechanical also concerns, and also heat transfer next to the electrochemistry for sure. So one of the ways to define, let's say, microstructure is just to basically, the technique that they use is fall and roll approach. Try to reconstruct the microstructure of the porous electrode, and then trying to validate that directly, indirectly with some experiments, how representative that microstructure really is. And then, of course, there's a compromise between the computational expenses and then the level of details you can get, and that's the reason some sort of aggregation in some parts of modeling is needed. For instance, like this cylindrical green box that you see to represent a group of particles which share some properties, or they are close enough to be to a little bit decrease the computational load, but still quite representative of the microstructure. The sort of validation that is quite feasible to do, for instance, is to come up and make juxtapose this particle size distribution that you can get from such a modeling with the particle size distribution of the active material, or let's say, which can be provided by the, let's say, the material provider. And that's quite very important, because at the end it's straightforward that it impacts the effective properties of your porous electrode. Simply speaking, tortuosity on a bulk way of thinking, but we can also look at it locally, tortuosity, and then tortuosity, of course, it impacts the effective conductivity, ionic conductivity, and everything. Yeah? So, and even in this case, impregnation of the electrolyte. Of course, there are lots of configuration that can be simulated once you have such a model framework set up, and then you can do some sort of sensitivity analysis, for example, to see what is the impact of basically the configuration of your percolation network, or what if there is an overlap between the active material, for example, NMC particles or not, configuration of carbon binder domain around the particles, and all this is basically defines the percolation of ions and electrons. So that sort of sensitivity analysis is quite very important. And in case of, for example, here, you could see also the impact of mechanics, also to see basically the effect of diffusion-induced stress, or diffusion-induced stress, and the vice versa, which a little bit is making the uniformity of the concentration profiles, lithiation, the lithiation front inside the particles different when that mechanics also is coupled. Yeah? So this is a good way to look at it. And also you can, for sure, look at how the, let's say, different stress components in your electrodes are basically evolving during the lithiation and dilithiation. For example, this corresponds to the previous slide, the same charge-discharge simulation, and you see basically your total static kind of pressure, which is basically defined by these three components. How it, during dilithiation, it kind of decreases, and then during lithiation, it rises. The second part, which is a little bit more related to the work which done in my team, is about you have models, and then how really you can measure some parameters directly or indirectly by coupling the models to experiments, so that you can have some access to the parameters which are difficult to measure directly. Particularly So the system is the same system, very similar to what Corson mentioned, and that's a kind of solid electrolyte, the next generation. So it's a very similar system to what Corson mentioned, described, but based on the LI-TFSI and I, not FSI. Yeah? So, and this is the system case study, and then we were interested to look at how the transport properties of such a solid electrolyte is sensitive to concentration of the lithium salt and basically a stack pressure. So that was the idea. More parameters, but what I show here basically is mostly about the LI-TFSI concentration and also the compression. And also besides, because today also we saw a lot talking about the ionic conductivity, but we should not forget about the lithium transference number, because ionic conductivity is a high frequency property. And for the performance of a cell, basically what matters is lithium transference number. Ionic conductivity is very high frequency. It's not for really battery operation. So we need to also be careful about the lithium transference number, which is also very difficult to measure, especially when you have multi-component systems. If you don't properly tackle the thermodynamics, what you measure is might be inconsistent. And so the important message here is that we see that the impact of pressure is quite constructive, both for diffusion coefficient, for a neutral combination of ions, lithium and TFSI, and also basically for lithium transference number. But for the ionic conductivity is not constructive. And then the idea is that, and we're wondering how we can explain also that, because there are not much theory about even irreversible thermodynamics theories that you can refer to explain the impact of pressure on the transport properties. So as such, what we speculate is that if you consider a moderately dilute solution theory or dilute solution theory, and we define some binary diffusion, binary interaction coefficient, we can call it binary diffusion, based on the concentrated solution theory or dilute solution theory, and then a simple hypothesis can explain that, and that's basically if we consider such a framework, then the experimental observation for constructive impact of compression and diffusion coefficient and transverse number, and the destructive impact can be basically explained by this, the fact that the pressure decreases the mobility of the effective counter ion to lithium, as a kind of simplification, while for lithium is constructive, the mobility of under pressure. And that's basically something that we could see also here and there in the experimental community, that they talk about this nano-confinement effect, which can have completely, when these ionic liquids and lithium salt get confined in very narrow channels, nanometric channels, this strange behavior of or non-uniform impact of, for example, transport properties based on the, let's say, the is it a cation or anion, has been observed. So that might a little bit explain. And sorry that I went over time, but there is no conclusion because the work is still going, and we have lots of challenges to deal with. Sorry. Thank you.
Yeah, thank you so much for your presentation. Next speaker will present related with anode modeling, especially this presentation quite interesting for sulfide-based solid electrolytes. Is Andrei Golov from CAC Energy Guna. Um,
Can ask him to share his slide. Andre, could you share your slides? We don't hear you. No, we don't hear you. We do not hear you, Andre.
His microphone is on, so it has to be something.
Perhaps you can leave and come again.
Online they can hear so the issues here.
I will check.
double check. Yeah.
Because my microphone is working and I'm not muted.
Yeah, we can hear you.
Yeah.
You can share your
Thank you.
presentation. Okay, great, thank you.
Just a moment. Can you see my screen?
Yes.
Okay. The topic of my presentation is interfacial property of erudite solid electrolyte at bar and coated lithium metal anode. All solid-state batteries have many advantages over liquid electrolyte battery. They can be safer, have high energy density, low surge charge, fast charging, and increased cycle life. A big challenge in the development of such battery is searching for ionic conductive solid electrolyte, which is compatible with the anode and cathode material. One of the promising candidates is the lithium thiosulfide chloride, on which we focus on this project, within this blade project. The main goal of this work is prediction, interfacial geometry, stability, and ionic diffusion characteristic of erudite solid electrolyte at contact with bar and coated lithium metal anode. To reach this goal, we applied following techniques and methods. To calculate ionic diffusion characteristic, we use topological analysis of procrystal electron density distribution. The generation of interface model have been done using lattice mismatch algorithm to study the effect of surface morphology on interfacial property. Additionally, we generate models with various electrolyte slab terminations. In total, we got 12 interface models with the 4 unique, symmetrically distinct crystallographic direction perpendicular to interface and various electrolyte slab morphologies. According to the result of the FT calculations, the erudite solid electrolyte is not stable in contact with lithium metal anode. Even geometry optimization leads to the composition of thiophosphate group and formation new lithium-sulfur, lithium-phosphorus contact. The MT result shows monotonically decreasing in potential energy, which is caused due to formation low energy product, the reaction between lithium and erudite. At 100 picosecond of MT simulation, we observed various intermediate product of electrolyte degradation, including partially reduced thiophosphide group, as well as lithium chloride, phosphide, and sulfide clusters. During the simulation, we observed significant change in the local atomic environment. In particular, the number of phosphor-sulfur bonds monotonically decreased with increasing number of phosphor-lithium and lithium-sulfur contacts. This is due to the decomposition thiophosphate group and insertion of reduced species to the lithium slab. According to the Bader charge analysis, there is electron transfer from lithium metal anode to the electrolyte because of the redox reactions. We observed the monotonic decrease in average atomic charges of phosphor and sulfur atom with the increasing atomic charges of metallic lithium, while the charge of lithium plus anion and fluor minus anion within the electrolyte stay constant. Based on the experimental data, the final product of the reaction should be lithium phosphide, fluorine, and sulfide salts. Based on this data, as well as applying the vector charge analysis, we can calculate the number of electrons required to reduce one formula unit of the electrolyte. Using this information, as well as the evolution of solid electrolyte net charge along the MD trajectory, we can calculate the amount of reduced electrolyte and find the reduction rate. According to this, the highest reduction rate observed for the last two models, lithium 110 or jaradite 110 and lithium 111 or jaradite 111. In the square bracket, the Miller indices of the plane is specified. So the difference in the reaction rate probably is caused by the difference in the surface energy of the jaradite in different crystallographic direction, because the surface energy of lithium is quite close. The morphology of the electrolyte almost doesn't affect on the reaction rate. However, it affects on the distribution of intermediate product of the reaction and overall the reaction pathway. Also, it should be noted that there is a strict relationship between the charge of the phosphor and sulfur ion and the type of the molecular group which contain these atoms. To study the effect of SCI layer on the ionic transport, we calculate the migration barrier for the bulk electrolyte as well as for the interface model. Here you can see at the top the migration map, the trajectories on which lithium can migrate within the interface. And at the bottom, you can see the value of the barrier at the bottleneck of the migration path with respect to the coordinate of the bottleneck. The higher migration path located at the ACI layer. This is because of the formation low conductive product due to the reaction of jaradite with the lithium. Though this reaction should increase impedance and decrease the battery performance. To overcome these issues and find a possible solution, we carried out additional simulation with 4 possible inorganic coating, including molybdenum sulfide, lithium fluoride, lithium phosphide, and lithium tin alloy. Opposite to interface without coating, geometry optimization of this model almost doesn't lead to any structural changes. However, after some time of MD simulation, we observe some electrolyte degradation for all models except for molybdenum sulfide. Nevertheless, the changes in local atomic environment much less than the changes for the models without coating. The vector charge analysis showed that for all coating except for lithium tin alloy, the net charge of the coating stay constant. But for the lithium tin alloy, we observe monotonical decrease in the net charge, which is caused by the tin reductions of lithium by lithium with formation more diluted lithium tin alloy. Comparing the reaction tree and the amount of the reduced electrolyte for all these models, we can conclude that the coating significantly decreased the electrolyte degradation. For all of this coating, we have quite high migration barrier, except for lithium tin alloy, which have quite low migration pathway along 100 directions. During the MD simulation, the migration barrier decreased due to partial amorphization of coating and thermal expansion. The highest drop in the impedance we observed for the lithium alloy. This is caused by the reaction coating with the lithium with the formation more ionic conductive products. So among all of this coating, the lithium tin alloy is one of the most promising ones. And additionally, to get information about the crystal structure of a solid electrolyte interface, we carry out long-scale MD simulation with the selenium dot or gyrodite structure, which is exhibit much higher reaction rate. And at the end of the simulation, we were able to observe the formation of the crystalline product. So this is the movie of the MD trajectory at the both side of the unit cell or the simulation box. We have metallic lithium in the middle. We have electrolyte, solid electrolyte, and the red region is show the crystalline product. At the beginning of the reactions, there is reduction of the electrolyte with formation of some amorphous product, but then start appearing the crystalline nuclei, which continue to grow and form quite thick SCI, which have a quite high crystallinity. So this is the main results. So we carry out the simulation of the of this model, and we found that our gyrodite is not stable in contact with the metallic lithium, and inorganic coating allowed to significantly decrease electrolyte degradation, and one of the promising one is lithium tin alloy. The main result of this work published in the following papers. So finally, I would like to thank our partners in Sublime project, as well as RSC and BSC for their providing computational facilities, and thank you for your attention. Any questions are welcome.
Okay, thank you so much. And today we have last speakers from CDTech, Diego del Olmo. He will present results from Safely Move.
And Teams, you have to share first. Did you do it?
Okay, so good afternoon everyone. So I will be presenting the part of modeling for the Safely Move project, specifically what we are doing right now at CDTech, and is mainly on the development validation for solid-state batteries with using macro-homogeneous models. So not detailed models as we were presenting for the other projects before, but more macro-homogeneous models of the whole cell. So this is okay. This is a bit the contents of the presentation. First I will start with the actual electrochemical model, and then we'll move to the mechanical model, which is actually the main development we have for the project. So the macro-homogeneous electrochemical model is basically based on this Newman type model. So it's like a pseudo two-dimensional model, as we call it, in which the cathode particles are, or like the cathode, this model as a both coexisting phase of a solid phase and a liquid phase, and we have the state variables on top of the scheme of the cell. I don't know if I can use the laser. Here. So you have the state variables in each of the domains. What we do in our case is, instead of the lithium ion type of models for lithium metal, we actually obviously simulate the lithium anode, and in our case we actually explicitly simulate the lithium anode. We don't just treat it as a boundary condition, but we solve the potential of the lithium metal, because we also will need it afterwards for the mechanical model. And then we'll see that the mechanical stresses that happen at the interfaces will modify also the reaction rates and the diffusion rates in the model. So what we have in particular in Selimove is that our solid electrolyte is actually a bit different because we also are using a separator to like support the solid electrolytes. We have to simulate these different phases also in the solid electrolyte. So these are a bit the results of the pure electrochemical validation. The parameterization was done for the individual materials also in Theotech and also in our partners. We can see here a comparison of some experimental C rates that are in the upper right corner that were done for a monolayer cell. So it was just one anode, one cathode, and one separator in a pouch cell configuration, and we can see that the model more or less follows the trend of the experiments, although it obviously fails at higher C rates, which in this case are like 3C, because we will see that there's a very low capacity already at 3C, and as you can see also in the upper right corner at 1C we have like also pretty low capacity. I should mention that it's also like results at 60 degrees, so it's at higher temperature. So in this case we have included the effects of the separator, as I was mentioning, only as like a macro effective property, so the whole separator is treated as a whole, and we have averaged the properties of the cell gas separator with the hybrid polymer electrolyte. So in our model what we have also included is some factor that takes into consideration the like inefficient or like inhomogeneous contact surface between the lithium anode and the actual polymer separator. So we have included these contact and roughness factors that simulate the roughness of the surface and the actual contact between the lithium and the solid electrolyte, which actually decrease the effective area for electrochemical reaction that is in the model. Okay, so moving on, based on this model we have also done some sensitivity analysis. So we have used this Sobol method for the sensitivity, which gives you some of these Sobol indices, which tells you what is the effect of each of the parameters in the actual result of the model. What we were measuring here is, if I'm not mistaken, is the actual capacity that we were getting. So it was the target parameter, the capacity that we were getting out of the cell. And the ranges that were chosen for the parameters were within like 1 order of magnitude above and below what we were measuring or what we were using for parameterizing the model. So what we can see here is that according to our Sobol analysis, we have the higher effect, or like the parameter that influences the most in our case, or what we calculate according to the model, is the diffusion in the electrolyte, so diffusion of lithium ions. And we can also see in the second graph that there's actually some high order dependencies between the parameters. So there's like the second order are the, let's say, the interrelation between the two parameters. So we have a high interrelation, so a high effect on changing both, for example here, the thickness and the diffusion constant and the conductivity and diffusion constant. So as I was saying, I conclude that mostly the catholyte, the ion transport or the diffusion of the ions in the catholyte is the main constraint. So moving to the mechanical model, which is the main development here, is like we have included on top of the electrochemical model I was mentioning below, also the stresses in the surface that are called that are caused by the deposition of lithium ions and also by the expansion and contraction of the lithium particle, the cathode particles upon lithiation and delithiation. So yeah, as I was saying, this causes some residual stress generation and it affects the applied pressure that we have in the cell. So this is a bit of the equation of the mechanical model and how they actually modify the electrochemical potential. As you can see here, the electrochemical potential has a term that depends on the stress, that is this sigma. And this change in the electrochemical potential causes also a change in the intercalation current density, so the Butler-Bormer current density here, and also in the diffusion within the particle, as you can see here. So instead of pure spherical diffusion, you have some modification terms that depend on the stress within the particle. So this is a summary of the whole model. So basically, as you are depositing lithium, you are increasing the volume of the lithium anode, and this causes an increase in the volume and therefore an increase in the pressure around here, because the strain increase and therefore will be related by the stiffness tensor to an increase in the stress on the whole cell. So you have, as I was saying, the lithium contribution and then the microscale contribution from the actual particles, where you have an increase in the hydrostatic stress due to the intercalation of lithium. So basically it depends on the difference between the average particle concentration with the surface particle concentration. So we have initially also validated this model with some literature for pure lithium-ion cells, and it kind of fits pretty okay. And also regarding the boundary conditions, we also have the possibility of using either a constant fixed apply pressure as boundary condition, or like constrain the displacement of the cell also that it doesn't bulge. So displacement will be 0 and the pressure will be changing. So for almost finishing, we have also tried to validate this mechanical model. For this, we have taken results from our partners in the project at Ikerland, which they have built this experimental setup in which they keep a constant displacement in the cell and they measure the pressure that is happening in the cell during cycling. In this case, we have I think it has C/10 charge and discharge, and we can see that the experimental and the modeling results more or less have the same trend. You can see here that at the end of the charge we have this constant voltage part that is not like linear with the model. But also I should mention that the stress at the beginning, or so the stress you apply to the cell is like 0.3 megapascal, so our model actually like underestimates, so and that stress it reaches almost 0.2. But we're also working in the better mechanical parameterization, because right now we are mostly using only literature parameters in terms of Young modulus and Poisson ratio. And also I should mention that this is right now a model for only a monolayer cell, let's say, whereas we are actually here, they are cycling a 1 ampere hour cell, which has, if I'm not mistaken, 6 cathode and 7 anodes. So the last part we're also working on a bit is some phase field modeling to actually simulate both the advance of the lithium metal interface and, if we can, the dendrite formation. We can see here some results that are actually not for lithium metal but for some solidification, and we can see this phase field model, how this structure can evolve, can simulate the evolution of the structures. And this would be like a 1D model, which includes also this Newman type model, and shows how is the advance of the lithium metal front as we are depositing or stripping the lithium metal from it. And yeah, that's mostly what I want to say. So in future work we want to separate this inhomogeneity that I was saying, that right now we are assuming it's macro homogeneous in the separator, and also improve the mechanical parameterization and kind of close back this loop with experimental results for validation. And that's it. So acknowledgement to all people at CETEC and at Salimov Partners, and that's actually it. Yeah, thanks.
Yeah, thank you so much for your presentation. We have time for question answers, please.
Thank you for a very nice presentation. I have a question related to the last type of modeling you were showing, the phase field modeling. Does that also include a component, so mainly the dendrite growth, then is that also influenced by stress in the system? And is that also included and reflected in the model?
Should I talk here? Yeah. No, right now, no. The dendrite model was actually initially developed in a master thesis, so mainly it was like including the Newman type model within the phase field model. So it was not stress related, purely electrochemical and
Okay.
phase field.
Thank you.
Thank you very much for the nice presentation. I have a question regarding this mechanical model that you presented. So do you also consider the decomposition of the active material, or for example the electrolyte that causes this expansion or contraction at the electrode level, or is it just based on the volume exchange of the active material?
Yeah, right now it's, let's say, doesn't include degradation, it's purely reversible, so it's just elastic with the active material. So the cathode particles that expand and contract, and the lithium ion that strips and deposits. So it's purely on the active material at the moment.
So it's not, you are not considering the, so You are not considering the volume change caused by the decomposition of the
No, the composition. No.
electrolyte. Yeah.
I mean, you consider the domain of the separator within mechanical properties for the whole cell, but not the actual decomposition of it.
Nice. Okay. Thank you very much.
I'm not an expert in modeling, but just a small question. When you apply the mechanical pressure, for example, can you find the sweet spot for the right performance plus long cycle life? Is that possible to do with this model?
Yeah, so that's something like we want to work in. We haven't had that much time to compare to the experiments, but as I was saying, like our partners are Ikerland are actually doing more experiments on this, and they are actually cycling the cells for a longer time. We want to compare that and see if our mechanical model can give you exactly what's the right pressure or how pressure actually affects the cyclability of the cells.
If there are also other questions for the other speakers, feel free.
Question for the previous presentation.
Andre, are you here?
Yeah.
No.
We cannot hear you again.
Okay.
Yes, that's
can I-
Sorry,
It's fine.
can you hear me?
Yes,
Yes.
yes.
Could I share my screen?
I don't know.
We can see you. It's perfect.
We can, my question is regarding the best interface. Your modeling detected that tin lithium tin alloy. Is it possible? What you model tell us? Is it possible to form it in situ, or should add a layer of this lithium alloy?
Actually, we can just deposit some tin on the lithium slab, and this alloy will form. So
Automatically.
actually, there is some experimental work that did such coating, and they investigate how it affects on the degradation, but with the other electrolyte. So it's possible to just deposit some tin at lithium metal, and this alloy will form.
In other words, how about particle size? How we can accommodate this particle size if it is formed in situ?
The particle size, actually, if you deposit very thin metal at the lithium slab, you will have probably quite a homogeneous monolayer of lithium tin alloy.
Okay, thank you.
Because all of the tin should react with lithium with the formation of this alloy.
Thank you.
Okay, thanks so much for presentation. We have quite nice modeling session, and we have last word from Maria Martin from CAC Energy Group.
You will get bored of me here all the day. So we have finished even before of time, so I was not expecting this. So I will just give some words to finalize this session. I would like also to share the agenda for tomorrow, so let me share it with you. It's in French, I cannot do it. Okay.
Yes. And then you can just go back.
Okay, for sharing the agenda.
I think you can keep it like this, but otherwise if you can use it.
Okay, it's fine like this, as far as they see it. Okay, so before closing today's sessions, I would like to thank all the speakers. I think that it has been a really nice opportunity to meet all the projects together and see where we are, where we thought that we were going to be 4 years back when we started, and how challenging is the reality of solid-state batteries and how the different projects are trying to tackle all these challenges in different ways with different chemistries. Also, I think it was really interesting, the topical session related to manufacturing, because I think that there are many things where we agree about the challenges of the lithium metal handling, the electrolyte manufacturing, the scalability, how to reach high ionic conductivity into the electrode when we are aiming to really thick electrodes with high capacity. So I think it was also good to bring all these issues here together and discuss about them, as well as from the modeling perspective, where we are talking about many different chemistries, so many different things to be addressed. I would like to remind to you that tomorrow we will have the third topical session. So last but not least, this is going to be related to sustainability and recycling. So actually together, tomorrow, the session or the day will be covering the new regulation for batteries announced from the European Commission. So we will start showing here in this topical session how sustainability and recycling has been addressed within the different projects in this cluster, but later we will go more into detail on how we foresee the future for this solid-state battery technology. Also, we will have the session related to the industrial session, again, addressing different points of views. From one side, we will have people coming from industry, but more on the material level, and also we will have people from the manufacturing or from the battery development. And let me check, I need to revise if I'm missing something else. Yes, sure, we will have the third keynote speaker tomorrow, so it will be Brekor. And this will be in the morning just before the industrial session that will be held in the afternoon. So this is all from my side. I hope that you have enjoyed all the sessions, also have the chance to discuss with people during the coffee breaks and the lunch break. And hopefully we will look for further collaborations to continue what we have started already with these projects. So thanks a lot to everyone and see you tomorrow. And thank you as well to the people that is connected online.